Okay, welcome to this webinar. Thank you very much for joining. This is the second one of the small webinar series on digital twinning, which is organized by Polis and AVL. As you know, this webinar will be recorded and it will be uploaded on YouTube. And please keep silent. And if you have questions, write them in the chat. What we're trying to achieve here is to inform you a little bit about our next e-truck project, which is focusing on electric trucks in peri-urban areas. And we also want to engage with the general audience, but also with experts. So we had our first webinar, which is a general introduction on digital twinning last week. And today we will give you a short recap of that webinar, and then we have a more deep dive with our expert, who is Leo Xenakis. And I will give the floor to him now to continue with our recap and then show us the tools that we are using for the next e-truck project. The floor is yours.
Thanks, Nicholas. Let me share. So... Okay, I hope you can see this.
Perfect.
Excellent. All right, so thanks for joining part two. Warm welcome from Graz. We talk about digital twins today again. A little recap of the last webinar. We'll go through some of the slides a little bit more quickly. Again, if you want a bit more detail there, I recommend you go back and watch that first part. So let's get into it. So this is me again. Spent about 20 years in automotive, 5 of those recently at AVL, half at OEM, and I'm focusing on collaborative research projects like Next e-truck to demonstrate some of the AVL solutions that we've been developing. So agenda for today, I'd like to recap, as I said, talk a little bit about Next e-truck. Again, this will be a recap, and then get into a little bit more detail around the digital twin creation framework and really the focus this time, some of the innovations. We'll look at some of the tools. So a quick recap. So if this is first time, then this is really some of the definitions we've got to get out of the way. So a digital prototype is what you would probably consider the standard models that you would use at the moment. It's like a start condition for digital twins. And once you have some data from the vehicles, which are kept in sync with these models, then you can call this a digital twin. And you can keep the models updated and in sync by relying on the digital shadow, which is this telemetry data, comes from the digital twins and is used to update the digital twins. And this is kind of done in 2 ways. We look at this, I like to split into online and what I call offline data. The online data is data that's sent from the vehicle. You can think of it as the sort of time-based data that's coming into your models. It's to simulate what is essentially happening in the near future on the vehicles. And the historical data is like the calibration or the parameterization of your digital twin. This is used to maybe over time, so this is months, look at degradation of your digital twins, for example, and make sure that that is reflected in the models, in the digital twins of each of those vehicles. So quickly about why digital twins. Again, I don't want to spend too much time on this. There's a lot more detail in the previous presentation, but essentially a lot of use cases. Obviously, if you have the ability to synchronize between the models that you have in the vehicles, there's a lot of use cases that are opened up between the fast digital twins and the high fidelity digital twins. Because they run at different speeds and have different accuracies, of course, they have different use cases. But just to quickly cover, usually the fast DTs are used for future prediction, things like fleet management, look-ahead controllers. This falls into the fast DT category. The high fidelity DTs, these can be used to diagnose more complex issues, usually have controllers built in. It can be used for even things like software validation. And one of the things I really should mention here is that you don't need to have to perform your simulations, let's say on the latest versions of these digital twins. You have a full record of historical models, let's say, of the vehicles at various different ages. It's a huge advantage to be able to look back through this and even to run simulations based on the age of the vehicle and the condition of the vehicle. And of course, you can mix and match between various vehicle components if you want, of different ages from different vehicles. And yes, certain things that you really need from the digital twins is things like high-speed comms or some of the advantage. You have this high-speed comms to other parts of the cloud. They don't need the communication to be all down to the vehicle. And of course, this allows you to offload some of the compute from the vehicle as well. And because you have all the vehicle data out in the cloud already, again, calculations that require interactions between vehicles, you can also perform these just in the cloud without necessarily having to do individual calculations down to, or requests for data down to each vehicle. So some of the key issues, you're going to have live communication between the cloud and vehicle. Talked a bit more detail last time, but really there's a lot of things which have to be considered here. You have data integrity issues, because of course you don't always have a good connection. There's security. You don't want this data to fall into the wrong hands. And also because we're sending commands back down to the vehicle, you need to ensure that this link cannot be hacked. So I've highlighted here, we're going to cover this in a bit more detail. So it's in red. We have some of the update methodology and how we first create the DTs. And then we're looking at, and then we have the traceability problem, but usually because we're using DevOps type pipelines for this sort of thing, everything has to be automated. You generally, if this is set up correctly, have traceability of which models, which parameters, everything that has been modeled, and also how the interactions have been with the vehicles. And of course, then you need to be able to automate all of this, because you could have thousands, if not millions of vehicles. Having manual steps here it's not really going to work. And as part of this, we'll be looking at, again, parameterizing and generating some of the updated DTs. Okay, and then we'll quickly cover the next feature projects as well, and then we'll take a few questions if there are any. So we got 18 EU partners here. It fluctuates a little bit depending on partners dropping in and out. 4-year project. We're about in the middle at the moment. We're planning to do 3 live demonstrators for 6 months. This was with 3 different OEMs. Unfortunately, you're probably aware Teva has unfortunately gone bankrupt, so we're looking for another partner there. And yes, as part of this, the digital twin development framework and also a full fleet management framework are in scope. Basically, any technologies that need to be used in the project will be either developed or customized for this project. And some of the specifics, so we have the Barcelona route up here for Irizar and a Ford route down here between factories, but essentially we're looking at these kind of specs for the vehicles. And the routes, and these are the sort of project goals. It should be noted here that the energy efficiency overall, this is for not just for the vehicle itself, but for everything. So it includes things like being able to charge at more efficient times, for example, more slowly. This counts towards the energy efficiency. Okay, so if there's any questions at this point, maybe we can take some.
We have not received any questions, so if you have further questions, please state them in the chat. And yeah, even during the segment, and then I can intervene if necessary.
Okay, so let's get into the main workflow of how we're developing and updating, deploying these digital twins. So the first step is, of course, to create plant models and the controllers. This has been done in MATLAB and in CruiseM. So MATLAB for the controllers, CruiseM for the plant models. If we have time, we can see very quickly how this tool works. There's a lot of sort of standard vehicle components in there, and you can pull them together and create vehicle models very quickly. These, in this case, are packaged into FMUs, fairly standard, high compatibility with many different tools, so it's great. And these can be pulled together and run inside of a co-simulation environment. We have our own tool here, Model Connect. And here we can run both high fidelity DTs and fast DTs. Fast DTs, they need to be developed or created through this Cameo tool. And because this is still in the simulation phase, you can choose, you don't need to input vehicle data as such. You can choose which cycles to run, what kind of vehicle data you want to put in. And the fast digital twins can be created from the high fidelity digital twins. So these are, there's a sort of one-to-one. We want calculations we need to run fast. Faster versions of the DTs are created from the high fidelity DTs. And then down here, we found that generally it's a much better idea to separate the model management from the parameter management. And what I mean by this is that the base model can have different parameterizations. If you keep storing these as individual models, it can take up a lot of space and doesn't generally make sense. You want to be able to freely, say, apply the same kind of parameterization to multiple models, for example, multiple generations of models. And so separating this makes sense. We're using GitHub for the model management and Krita AVL tool for the parameter management. And what's good about all this is that generally end users, they can have a nice interface to maybe only one tool, probably Cameo in this case, or you could go down to Model Connect if you want. And you can have the environment set up automatically, and you just look at these front ends to run whatever tests you want. And we saw last time the front end to run this. Please have a look at that if you're interested. Once the real vehicles are available, then again, of course, you can manage the parameters and even the for the XCUs, you can manage the calibrations for the XCUs also in Krita. And you have Device Connect, which is our secure communications hardware and software framework for pulling and sending data to the vehicles. Concerto for post-processing of digital shadow data. And we have some algorithms and extension of the tools available in Cameo that allow us to update either the high fidelity DTs or the fast DTs. Again, this can happen automatically, of course. And we have this automation framework, DevOps Pilot, which is developed together with Microsoft to do this. Again, the end users really see a nice web interface. Don't need to worry about the complexity behind, and you can pull together any tests, any parameters, any models to run them in any way you want, as well as run custom workflows such as updating the DTs. So let's, well, maybe any questions on that or?
No, you can continue, but I encourage everyone to post their questions.
Okay, good. I hope this means you understand. Right, so let's focus a little bit on part of this where we're using Cameo to first create the fast models from the high fidelity models. So this is where you've got the high fidelity model here. Oops. Here in the middle, and you're running this in simulation and using Cameo to send some variation parameters to this model and creating a fast model from this. So just a little bit of background about Cameo. Sorry, let me just get it's a bit noisy. Right, so just a little bit of background about Cameo. It's a tool that allows you to test in all different environments. So hence the safely here. So physical, semi-physical, simulation environments. You can run tests in all those environments. It allows you to understand component systems by making these sort of empirical models of the behavior, these behavior models we call them. Essentially a characterization of components and systems. And once you have these faster models, then you can also use these to optimize. And if we have time, we'll have a look at that as well. It's just a list of all the environments which are supported. It's worth mentioning here that there are tools which are, of course, very good in simulation, or have been optimized to work in a more physical environment. Very few tools out there, I think, that span these quite seamlessly. Cameo is one of them, I think. So if you're trying to do optimizations, and optimization is a very broad word here. I mean, in this case, for example, we're really trying to optimize the delta between the full fidelity model and the fast DTs we're trying to make. But when you're doing simulations or any tests really, you've got all these questions. I think these should be familiar with most people who are doing simulation, for example. What do you do about these? How do you know if you have enough tests done? What about input ranges? How should you distribute your test cases? What do you do with your input variables, and how many input variables should you have? Cameo allows you to do this with very little input, and hopefully we'll see a little bit of this. So just to show the general workflow of what we're about to show, you have your tuned high fidelity digital prototypes already. You're going to do some DOEs, DOEs design of experiments. So this is where you're choosing which input variables or stimuli you're sending to your simulation in order to run things. In this case, we're running cycles. Cameo can automate the generation and the execution of these tests. And then you can automate the fast model tuning here. And hopefully at the end of this, you have some tuned fast digital prototypes, and the errors to the DOE data you generated here, basically the error to your original high fidelity digital prototype has been minimized. And in this case, basically running cycles, like I said, so you're looking at the output traces of the cycles, and the output trace from this model and this model should be as close as possible. And of course, you can use Krita to store your parameters for the digital twins. So this one's a bit of a complicated slide, but hopefully it's relatively simple in the sense that how we try to create the digital twins is to have an initial calculation that happens just to get the, sorry, give me a second. To have the force of the wheel calculated, this is just physics. So this is an internal calculation. And then some of those inputs which are put in here are also put into the model for the power that's consumed by the battery. and also the power that's consumed by the auxiliaries. These blobs show how we did the tests, which variables we actually changed in the first step that I'm about to show. And once we integrate all of this up, then we can see how much energy is needed, and then we can calculate this into a delta SOC. This will hopefully become a little bit clearer in a second. So let me just carry on through.
I have a question
Sure.
because there are no questions in the chat. Do you think that these or from your tests, these parameters like wind direction, for example, can these have a significant impact on the vehicle range, or is this from your experiences, or are these just like minor yeah
Well, I
minor
suppose,
parameters for the simulation?
yes, definitely. I mean, wind speed, or so when you're just driving the vehicle normally, you know, the vehicle speed as you go up and up, the amount of fuel that you use, if it's a normal vehicle, or the amount of energy you use in an electric vehicle, this can go up really quite a lot, especially when you're at higher speeds. And this is because of the air resistance. I mean, when you're riding a bike, for example, you feel this. And of course, with a truck, you have quite a large frontal area. So, you know, the wind can contribute quite a lot to the energy consumption, especially because roads also can be almost like a corridor sometimes for the wind. And you know, maybe on average it averages itself out, because you know, maybe if you're going in one direction it's a headwind, but then in the other direction it's a tailwind. But you know, we're trying to do a little bit more here than maybe has been done in the past, so we're definitely looking at this as well in terms of how it might affect the energy consumption calculation. And yes, it's been quite interesting in that you know, trying to get this data, for example, is quite hard. Usually you have to interpolate between weather stations, which are quite far apart usually. And like I said, the roads themselves can sometimes form these channels, which you know, might not be reflected within the weather data that we have available. So you know, this is going to be an interesting challenge when we integrate this. Okay, if that's it, then we carry on.
Yes.
So what we did this time is we developed some cycles where we have the velocity changing sort of slowly. So we have a slow acceleration and a slow deceleration, a fast acceleration, fast deceleration, and so on and so on. And then this is repeated at different conditions. So some of these input conditions here, for example, can be varied, and we'll see a little bit later how there is some intelligence here in terms of how these can be changed in order to give good coverage, because you don't really want to do a full factorial. So you know, covering all the different combinations if it's not required. And we'll see how the intelligence built into Cameo is helping with this. So I think we'll maybe switch over to, yes, let's switch over to Cameo to have a quick look. So hope you can still see this.
Yes.
So I'd like to show here, for example, that, well, we've basically done a lot of cycles. So you can see each one of these. So we've kept the ambient temperature fixed here. And this is the vehicle velocity. You can see we've done many cycles with different ambient temperature input.
Since this is very small for the audience, maybe you need to explain what the X and Y axis of each of these segments show. And
you know what? Maybe
or you
should.
can make it bigger, but it's the rest is very visible.
Let me just share the other screen. I think would be better, because sorry, I put it on the enormous screen. Maybe this helps a little bit. I don't know. Is that any better, or?
Yeah, I think so, a little bit. Yes.
Okay, but we have the time axis along the bottom. We basically concatenated all the cycles that we've run. And we can see here essentially the inputs that we used to the models. So what we really varied was these, the vehicle speeds that we saw, and we fixed the ambient temperature for each of these. And you can see here, for example, that we have a delta between the coolant temperature and the coolant temperature for the battery and the actual battery temperature. We have the same thing for the cabin here. The cabin air temperature versus the or minus the actual cabin temperature. And here we see the force at the wheel. So you can see we've done the calculation already for the force at the wheel, and yeah, and use this as an input to get to the battery power. So, well, yeah, you can easily import data here, have a look at it, choose which are variations and choose which are responses. And there's lots of different plot types that you can look at here as well. Get rid of this. And once we've sort of sanity checked the data here, then we can move on to the modeling, which is probably the more interesting part. So, of course, you know, you can automate all of this. The testing, you don't need to be there for this. Here, in order to build the models, you just go here and you just hit build selected. As you can see, it took about a second, even though we have about 20,000 data points. So it's pretty fast. If we go to the graphics again, there's a particular type of plot here, which we call the intersection plot. This allows you to query exactly what your model is doing. So you can, in this case, we have a 3D model. I mean, initially it was a 5D model, but we can look at those other ones later. I'm trying to reduce the number of inputs here so that it's a bit easier for you to understand what's going on. But basically you have at the bottom here, these are your inputs. So you have your total wheel resistance force that we talked about, you've got ambient temperature, and you've got your vehicle speed. And even though Cameo itself knows nothing about the vehicle model we were just testing, you can work out a lot of stuff from this. So just as an example, you can see that here, for example, if we change the vehicle force to 0, you can see that the vehicle speed has almost no effect on the energy consumption, exactly as we would expect. I'm sorry, I should have probably explained that on the left here, we have the battery power that's being modeled from the vehicle. And a positive value here is recuperation. It's energy back into the battery. And negative value is, of course, the driving force. So again, if we look at this, we can see that we see what we would expect, right? As the vehicle speed goes up, you're using more and more energy. See this here. And if we're recuperating, you can see that as the vehicle speed goes up, you're basically recuperating more energy. So you see the power being used to charge the battery going up. And also here we can see a few other things. So for example, here, we would really expect that when the ambient temperature is very high or is very low, the cooling system needs to work a lot harder in order to get rid of this this heat. So, or if you're in a very cold environment, you're using a lot of energy to heat up some component like the battery. So we can see here that, yeah, at around the sort of comfortable set point, both for the cabin and for the battery, that energy consumption is the least, and you're using more and more energy as you move towards the edges of the temperature range. And yeah, of course, it's quite interactive. So you can use this to really explore the behaviors that might not be so easy to spot. If you have, you know, up 5, 10 inputs, this becomes a much more complex picture. And being able to see this easily is quite a nice advantage. We can also add in some of the delta battery stuff if we want. We might have time to cover in. But here, for example, again, we can see that at the edges of the cabin temperature window, you're using more or less energy. And actually, we can see some interesting phenomena here as well. So if you're at a sort of very big delta between the cabin and the set point for the cabin, then you might have to use more energy. For example, over here, because both need to be cooled. If you have an opposing trend, then maybe you can take heat from the cabin to warm up the battery, for example, or vice versa. And this leads to less consumption of energy. Oh, I probably should explain a few things on these graphs as well. The green bar down here is showing where the model is valid. So if you move outside of this window, which is, of course, it's a variable window because you don't have absolutely full coverage of the areas that we were interested in necessarily. And if you go outside, then you can see the model quality is dropping away, and you see these error bands or these confidence bands that are expanding. Okay, any questions about this?
Not not in the chat, but I have a question.
Sure.
When you're moving these lines and then these error rate are occurring, are these already relatively significant, or is the potential error relatively small? Because I don't know the model. Yeah.
Well, it's quite difficult to say. Obviously, it really depends on how you look at the data. What's interesting here is if you look at the model, if the model and the data that you're trying to fit is perfectly modeled, then you wouldn't expect any scatter here at all. But in this case, we're looking at quite dirty data from it's a simulated vehicle. In this case, it's going to be even dirtier when you simulate on the road, and you're really looking to capture the average behavior. And you're a little bit high, a little bit low, depending on the prediction here. But overall, you're basically drawing this model line through the data that on average should give you the correct answer. So if you look second by second, you can actually be out by quite a lot. But this isn't really the point of this. This is, you're not trying to have absolute full fidelity here. You're trying to work out actually on a second by second basis. So we're not even using the 10 Hertz data here. I'm trying to work out on that sort of scale over over cycles, which is maybe 30 minutes. We'll see some data, some plots later that show that we didn't use any of the cycles or the simulated cycles of the Barcelona route, for example, or the Turkey route, and after 30 minutes or an hour, we're within a few percent. So generally, the prediction I think is very good, and this is just a preliminary version. So over time we will refine this also.
A quick follow-up question, but then your requirements for good quality data between our two cities would also be different, because I think between the two depots where the truck drives in Istanbul is probably much more even, whereas when you have like urban traffic, there will be much more variety, I assume, because of like starting and stopping and.
Yes, interestingly, so this is obviously just for the initial parameterization. So when we're looking to update the DTs, this kind of data, if anything, the dirtier data is more useful, because you have lots of different input conditions. If you just steady state on a road, just doing 40 kilometers or 60 kilometers for ages, this is not really providing much variation in the inputs. So if anything, you want this kind of data, but of course this potentially proves more problematic for the data processing part. So if you have lots of stopping And starting, you need to cut out a lot of these stops, for example, where the ignition is off, and pre-process the data. So this can also cause a problem, especially for sort of delivery type cycles. Okay, we better get moving. So hopefully there's no other questions, or
you can continue.
Okay, so we go back to the presentation. Okay, so just to show a bit more clearly some of the intelligence that's provided here. So for example, we had temperatures that we could change. We could have changed mass, for example, but knowing the ranges and which test cases, so which input combinations you're going to test, can be quite difficult. And here, for example, we see some examples where if you try to just have a uniform distribution of the points on the output side of the spectrum, so there's the input and then what the output does, and you can see here, for example, that uniform point densities can lead to maybe enough data here to capture the trends, but absolutely not enough here. And if you go to the other end of the scale, you've really got far too many test cases here. So basically wasted simulations are not giving you any data at all. But over here, you need this density of test cases in order to capture the capture the trends. And really, you want to do this sort of thing, and hopefully we'll see in a second how this is achieved by Cameo. But yeah, not having to think about this sort of thing can be extremely useful, and also allows automation of this process without the process becoming extremely long because this intelligence is built in. So just to sort of summarize, there's actually two types of models. We only looked at the empirical, as you saw, basically required no setup. I didn't do anything. I just set it to this automatic 2 modeling type. I took the input data, told it which was the inputs and the outputs, and we managed to get the models at the end. But if you want to constrain them through some physics, so maybe you want to, you have some relationships which are known already, you can use Cameo to build a semi-physical model where you've constrained things a little bit more. And again, then you can reduce the number of points that need to be tested even more. And as Nicholas was asking, how did this work out? We tried a variety of different cycles and a variety of different conditions. So we have I think it's the Barcelona at the top and one of the Turkey cycles at the bottom here. And I've offset the actual and the predicted here, so you can see. Otherwise, they were basically on top of each other, so you didn't really see where they were. But yeah, in a lot of these cases, we had error in the sort of 1% range, but in all cases within 3%. So I think this is pretty good. One of the things I should show quickly is you can actually export a lot of these models very quickly. So you can go here and let's just create a new folder. Models. Go get this. You can export to a lot of different types, but let's just take in Excel maybe. Support Python models as well. See, this is quickly exported. The folder. Go into Excel. One of the things I really wanted to show here was there is something called the hull. We'll see a little bit later how this is used, but essentially this gives you a prediction of how close you are to the edge of your model. So if you're at 1, it means you're kind of at the edge. Anything above 1 here for the hull, it means you're extrapolating from the model. Having this as an output of the model is extremely useful, so you can tell almost immediately whether you can trust the data that's coming out. So Maybe we can change some things here. Let's say, I don't know, 10 degrees. And you can see that in this case, we've gone outside of the hull, sort of thing. Oops. We'll keep the other stuff the same. So yeah, if you put in the cycle data here, for example, you can immediately just simulate the whole cycle, even in Excel. And you can see here, for example, that you're well within the hull. These outputs here of the power can be trusted. As you're starting to approach the edge of the model, it becomes less sure about the output. Now here, I wouldn't really trust the output at these conditions. Okay. So we go back to yeah, so we've seen this, some of the advantages as we saw, we've got this built-in model error prediction. We can export to lots of different model types to integrate into different environments. And again, most of this can be automated through a DevOps pipeline, but of course there is some development here that we're doing on NextDtruck to make this a little bit nicer. Because of course we can't just show what we've well, there has to be some development on this project also. And yeah, here we saw the inputs and how these inputs are then giving us the battery consumption prediction there. Okay, I think we're running a little bit short on time, so we've got to maybe cut some of this out. But essentially, when you have that full fidelity digital twins, there's a particular task which tends to take up a lot of time, is quite difficult to do, and this is to auto-calibrate maps. And so one of the things that Cameo is able to do here is to automatically change the map shapes, and of course use the intelligence that is built in to not just randomly generate maps, but to see which maps are giving the best match for the data that you're trying to so that the component parameters that you're trying to match here. And yes, when you're close enough, it will automatically stop and say that the maps have been essentially parameterized or calibrated. And this particular workflow is not something that we did on NextDtruck, but is kind of like a first step. You tend to have a component test bed. Again, you're doing some tests on this, and then creating these high fidelity models, or I should say updating the parameterization of these high fidelity models, and this gives you your tuned high fidelity prototype. And how this kind of works is, this is something that you can also do for controllers. So you can tune PID maps, for example, but essentially you have this auto generation of maps. You can simulate a cycle, see what sort of what you should have got versus what you got. You can work out all sorts of KPIs. I mean, if it's a controller, maybe some of these make more sense. But essentially, you're looking to have some kind of key performance indicator on what the error is between what you should get and what you are getting. And then this trains the behavior model. And based off of this, map shapes which are much closer to reality compared to not are prioritized. And there is an algorithm that allows these map shapes to evolve, and new maps are generated, and the cycle continues until we're happy with the output. So I don't think we can go into too much detail, so I'm going to skip a few slides here. Essentially, you're probably thinking, how does this actually work in reality? because usually what happens is unless you test something, you can't really know what the behavior is going to be. And generally what happens with a lot of this type of testing is that you will fix your test parameterization already at the beginning. You know which combination of inputs you're going to test here. You'll run your test, and then in the analysis, this is where you gain a lot of the information about the behavior of what you've just tried to test, to characterize. But this isn't a very efficient way of doing things. You can see there's all this information that you're getting from the test, and you're not really using any of this. And so you're really unsure about, whether you've put the correct inputs even, or the input ranges, is the point density high enough? And all this knowledge is essentially wasted. We won't go through this. But essentially what Cameo does is already, while the test while the simulations are running, it's using the information that's coming from each of these, each of the simulations that you've actually done. It's already building an internal model. So a sort of dummy model internally. And based off of the information from this, it can say, well, these combinations seem to be giving me a better result. Auto-generate, new test cases and carry on the test until you've reached the targets that you were looking for. And this can be used, of course, to match between some desired output and sort of the output you're actually getting from the simulation, but it can also be used, of course, for things like optimization. So if you're trying to optimize the energy consumption of the vehicle, for example, and you have the ability to change, for example, the control strategy for the heating system. This is something that we're doing on this project. Then this is something that could also be done with this kind of algorithm. So, well, just to quickly summarize some of the benefits here, you don't need to significantly limit the number of inputs on when you're doing this type of test, because if there is no significance to those inputs, so they're not having a big effect on the outputs, then FTDO will automatically reduce the variation on some of those insignificant inputs. So you can put more inputs than you were than you think might be possible to put as inputs, and the unneeded ones will just get whittled away. Again, the same thing with the ranges. You want wider ranges to cover a big area in terms of characterizing the thing you're trying to model. Again, you don't need to do this because ActiveDO will automatically change the ranges on your inputs if it's not covering what it needs to. We talked about the point density, and at the end, when the delta, or when you've found optimums, this sort of thing, you can set some thresholds as to when you as the engineer think things are good enough, and you can have Cameo automatically stop testing at that point. So I don't know if there's any further questions here, but if not, I'd like to cover one last thing.
Yes, there's a question.
Yeah.
Will the material be made available? I can answer this. Theoretically, there will be the webinar recording to be published on YouTube in the next couple of days, where I also write a short news item on nextetruck.eu, which is our homepage, which I will share later. And yeah, our attendee Pascal thanks you for this interesting session, but yeah, he would like to access this information.
Yeah, and I'll mention at the end as well, but
yeah,
if there's anything that you want to know more about, then we can do more demos, we can do specifics. I'm really trying to do an overview here, and I realize that we're trying to cover a lot of material, so sorry about this, but anything of interest, you let us know. So just to quickly finish up here, so if we're actually going to the proper digital twin bit, let's say, then this is the workflow. So you have the vehicle data come in, you have Concerto do the data cleanup, and Cameo can then retune either the high fidelity prototypes, which so this is the very first step where we have going from simulation to the real vehicle, and then once you're out in the field, then you're retuning the digital twin again to a new digital twin, and the same down here. And this is where you minimize the errors to log data. What I'd like to cover here, just because it was an interesting thing that we found quite interesting, was that when you create your base models, you don't necessarily have, you have the ability to control your input, so you can cover the full design space. When you're running the vehicles, you don't know which part of the design space you're going to cover. The vehicle's going to run what it's going to run. You can't specify what the vehicle's going to do. But this means that if you then try to update the models, you can only update them really in a certain area. So this is where this model validity comes in. So you can automatically see where the model is valid. You can see your calculated delta. You can apply this on top of your base data and only update the areas in which you have new data and ignore the outside areas because you don't have new data here to add. And this was made much easier by some of the functionality that was in Cameo. Okay, we won't cover this. I think we're a bit short on time. But essentially, yeah, we integrated some of the controllers here into some of the models too, because they're very fast running, and split the models into pieces, which helped to increase the fidelity and also reduce the testing requirements in terms of data input to parameterize these models. And yeah, when we really get the vehicles, it'd be interesting to see how much easier this makes things and how it helps with the fidelity. I'd just like to finish with, these are just some of the SIL partners that we're allowed to talk about. There's many more we're not, but there's been lots of different projects ongoing. Some of them are digital twin related, some of them slightly less so. But yes, if there's anything that you want to know more about, then just let us know. So this is just a quick overview of all the tools in our AVL suite, but it's AVL policy to also support third-party tools. So most of these tools will interface with other tools, and depending on the customer, sometimes we'll develop custom interfaces as well. And just to finish here, we have the Experience Cloud, we call it. This allows you to have a look at each of the individual tools and also request demos. So yes, if you have time, please have a look. Right, well, that's kind of it from me. I think there's going to be a little bit more from Nicholas, and maybe we have time to take a few questions at the end. Apologies last time. Maybe we didn't leave time for some of those questions, so please feel free to give them now.
Yeah, please state them in the chat again, and or maybe even point out if there would be some aspects that we should highlight in a potential further webinar, or alternatively, of course, you can write my colleague Leo. Obviously, I will just give you a short wrap up of our webinar and some further info. So we hope that you keep in contact with us. There are 3 channels. The main channel is our website, which you can find by using the QR code here on the left, and the homepage is nextetruck.eu. There you can find all public deliverables, all news items, events where we're going to speak, and the use cases, or if you want to call them the pilots, which are currently the confirmed ones in Barcelona and Istanbul. And there you can also find the recordings of both webinars in the next 2 weeks, where we write short news items about them to summarize them in a brief way. And then, of course, we have our social media channels on Twitter or X, x.com/nextetruck, and also LinkedIn. We're also very active with more than 500 followers. What I would like to say is, if you keep engaged with us, there is potentially another webinar coming up on megawatt charging that we are organizing with our partner that is the expert on that topic. And this is going to be planned in the end of October, where we've just received some confirmation emails that this will be possible. So yeah, keep engaged with us, and then you can learn even more. Here are our emails in case you have specific questions to either me as the project manager from Polis related to communication and dissemination, or my colleague Leo Zanakis from AVLAT. So I will stop it. Do we have further questions? This doesn't seem to be the case.
Well, since we've got a few minutes,
Yes.
maybe we could very quickly just show. So I thought I might not have time, so I didn't show it.
Yeah, that's perfect. I mean, we can.
Yeah, so a couple of minutes on this maybe. So basically, this is Cruise M. So you can see here, for example, that we have a lot of different components that you can just choose from and just place in. And there are higher fidelity and lower fidelity ones, depending on how much data you have to parameterize. If we look here, this is a high voltage part. We can look at the e-motor, for example. You can see you put a load of parameters, load, losses, and quickly wire them together. And yeah, this allows you to very quickly create a vehicle and really start testing if you want. I just want to, yeah, well, show that really. And we can see here, for example, that we also have, fuel cell already in here as well. And also some simple controllers as well if you don't have those, but generally this is really only for the base vehicles. The controllers generally have to be built somewhere else. Okay, well, that's it. I think we're just in time. Well, any final questions maybe here, or?
No, it doesn't seem to be the case. So I'm now concluding the webinar, and thank you very much for your attention. And we hopefully will see you at one of our upcoming events that we are planning next year, or the webinar that hopefully will take place at the end of October. We will keep you informed, and we wish you a good day. Thank you very much for joining. Bye-bye.
Thanks, everybody. Bye.